In this video, we're going to review some key ideas about the way science is done, the scientific method. We're going to look at some key terms that are used sort of with reference to the scientific method, talk about describing it and applying it, and really this is sort of a philosophical and conceptual basis for everything we do in chemistry and in science in general. Everything in science is empirical, right? Scientific knowledge is based on observation and experiment. And you may have learned in grade school that there's sort of a canonical process for this. Now, real science is often a messy version of what you see on this slide, but it gives you sort of a Platonic, idealized sense of what science is supposed to look like. We start with observation. We look at stuff. From looking at stuff, we develop a hypothesis, an idea about why the observations are the way they are. To test that hypothesis, we develop and carry out an experiment. And that experiment, again, hypothetically, in a highly idealized world, either supports the hypothesis or is inconsistent with the hypothesis. And if the latter result is observed, then we go back and revise our hypothesis, come to a new hypothesis, carry out another experiment, and basically go around and around and around and around in this circle until we get evidence that supports whatever hypothesis we end up landing on. So there's an evolution of hypotheses that happens over time. Often we'll come into the experiment point right here with the development of new technology as well. New technologies can enable us to develop and test new hypotheses, really starting the cycle at the point of hypothesis. Or maybe we had things that we wanted to test, ideas that we wanted to test, but the technology just wasn't there. The technology is developed. We get into a new experiment. Now, if experimental evidence supports the hypothesis, we try to collect as much of it as we possibly can, and then the hypothesis over time gets put together into a theory which is a more robust model than a hypothesis. A theory is, you can think of it as a model that's going to apply over a wide variety of experiments, and it's got something to say about the way the natural world works in general, a scientific theory. So more detailed definitions for these terms are shown on this slide, and I'll just point out a couple of things that are over and above what we've already talked about. So a hypothesis, we've mentioned, is an explanation of our observations or an interpretation. And good hypotheses are what we call falsifiable. We should be able to collect evidence that indicates that they're false, allowing us to rule them out, essentially. And we do that, we collect that evidence through experiments. Experiments are highly controlled procedures, controlled so that alternative explanations other than our hypothesis of interest are minimized. Now, in modern science and in the social sciences, experimental control can be very difficult. And so often what we're doing there is actually comparing different hypothetical models. And there are statistical tools that allow us to do this, but we try to control as much as we can to avoid those complications, minimize the complications, and the experiment's going to support or refute the hypothesis. As hypotheses pick up experimental evidence, they develop into models for the way that nature is, these scientific theories, and theories can be predictive. They predict behavior beyond our current observations that, for example, we can test in later experiments. Dalton's atomic theory being a classic example of this, a theory that existed way before we had direct, for example, visual or submicroscopic evidence for atoms, but nonetheless predicted that matter was going to behave as if it is made of these tiny, indestructible particles called atoms. A law is a statement of past observations that is common to all observations. Scientific laws are relatively rare. In chemistry, the only natural laws you'll see are related to this idea of matter being neither created nor destroyed, and then the laws of thermodynamics, which govern how energy works and energy transfers work, more or less. And so the example on this slide is the first thing I mentioned, the law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed, it only changes form. And laws, just like theories and hypotheses, are subject to experiments that can add support to them or prove them wrong. However, because laws are often decades, sometimes centuries old, they generally are things that we take as axiomatic in the course of our experiments. We're not going to expect the law of conservation of mass to ever be violated in the course of a chemical reaction. So we think about things like mass balance. If some mass has disappeared, I can ask the question, where did it go? And think about things like maybe a gas was generated, or maybe I accidentally discarded some of the reaction mixture, things like this. The graphic on this slide gives us a sense of how we think about observations, laws, hypotheses, and theories sort of in a categorization sense. So observations give rise to laws, the laws of nature. Commonalities to all our observations eventually become this sort of ossified set of laws, like the laws of thermodynamics. Within the category of testable explanations, we have hypotheses derived from prior observations. There's sort of a connection here between observations and hypotheses. And within the realm of hypotheses, related hypotheses are often put together into theories, generalizations of a set of hypotheses that give rise to an overarching model. So a hypothesis can become a theory or part of a theory, but the theory remains a model. It's distinct from a natural law, which directly refers to observations. A theory is an explanation of a set of observations. A law is a principle or concept or idea that observations must follow. So here we've really just begun to scratch the surface of how science is done and sort of developed this highly idealized model of how science actually works. The real process of science is quite a bit messier than this. However, as you're starting to learn chemistry, this is really how you want to think. You should be looking for empirical evidence for all of the theories, models, natural laws that you come across in your studies of chemistry. And there will be quite a few. And at the root of all of those is empirical data and empirical measurements. And this is key to science as a practice and as a philosophy.